We can paint the world a beautiful picture, holding out for everyone to view.
This lesson is going to take a look at working with function notation. We've already discussed a little bit about function notation, and usually we talk about functions with the letter F. But if you use a graphing calculator or any other software, oftentimes if you graph more than one function, it will give each function a different letter, a different name. So you could have f of x or g of x or k of x or h of a, etc. As you can see from the examples here, f of x could be x squared, and then g of x would be 2x plus 4, h of a. It's saying I'm going to map x to x squared. This would be like y equals x squared, etc. This is a way of representing the y value, especially when we're graphing it. And sometimes you'll even see the graph labeled x and f of x when you're just graphing that one function f. If you're graphing several, then you wouldn't see several different axes. You would usually just see a y-axis. Let's take a look at the different notations that are possible also. These notations in the box all mean the same thing. So you could see y equals x squared plus 7 or f of x equals x squared plus 7. These are the most commonly used. The others, however, you could see somewhere in a textbook or on a worksheet, and it's just saying if I take x and map it under the function f, I would get x squared plus 7. Also, we have the f such that, remember this from set notation, I'm mapping x to x squared plus 7. And the last one, again, we have another such that with this line. So I have the function f that takes xy such that y becomes x squared plus 7. They're just different notations and things you should be exposed to, but again, oftentimes you're going to see one of the two most frequent notations. To work with function notation, we're just going to substitute in. It's actually pretty basic, but sometimes students get a little confused by the notation that's used. So if we represent a function in number 1 by f of x equals 2x plus 5, we want to find f of 3. We want to see what happens when x equals 3. We'll replace the x value with a 3, and we'll get 2 times 3 plus 5, which is 11. Now this answer 11 is the image of 3 under f of x. What does that mean? It means we're graphing the point x is 3 and y or f of x equals 11. Go ahead and work on number 2 for h of x when x equals 4a, and we'll get an answer in terms of a. If you work out the algebra there, you'll get 2 times 16a squared plus 24a minus 3, and the final answer would be 32a squared plus 24a minus 3. Number 4 instead of number 3, because we decided to skip number 3, I'd like you to evaluate f of 3h plus 2 when the function f is x squared plus 2x minus 1. So go ahead, plug in, and see what you get. If we evaluate that and square our binomial appropriately, we get 9h squared plus 12h plus 4 plus 6h plus 4 minus 1, which simplifies to 9h squared plus 18h plus 7. Now composite functions are something you're going to also see. This is where we're evaluating a function of a function. So I'm going to go over this with you a little bit, and then I'm going to let you work on just practicing using function notation. So the term composite of functions or composite function refers to combining functions in a manner where the output from one function becomes the input for the next function. The range, which is our y values, becomes the domain of the next function. And composite notation you'll also see with composite transformations and other things in math. And this is read f of g of x, or it could be used with the parentheses. So I'm taking the function of g of x with f of x, and it's read f is composed with g of x or f of g of x. You'll most commonly hear people say that. You have to be careful with this because the innermost parentheses are done first. So we're working from the inside out. So let's look at the first example. Given the function f of x equals 5x and g of x equals x squared plus 1, find f of g of x. What that's saying is I want to take f of what's g of x? X squared plus 1. Now f of x says to take that and map it to 5 times x squared plus 1. So f of g of x is 5x squared plus 5. Let's take a look at g of f of x. G of f of x says I want to square x and add 1. Well, that's going to be a 5x. So I'm going to take 5x, square it, and add 1. And so I get 25x squared plus 1. In making an observation about that, is composite function commutative? Well, absolutely not, because f of g of x is not the same as g of f of x. So why don't you try example 2 down here. Find p of h of x and h of p of x. P of h of x is going to be x squared plus 2 because I'm taking the p function which takes x and adds 2, but I'm plugging in an x squared. H of p of x is going to take x squared plus 2 and square it. Again, notice you're doing this part first and using that for the input for h. The last type of notation that you might be seeing is inverse function notation, and it's a little bit about inverses in the last video, but the notation is going to be f to the negative 1 power, it looks like, of x, and that's saying I want the inverse function for f of x. And to get the inverse function, what you're going to do is you're going to say this is kind of like saying y equals 3x plus 5. Now I'm going to swap my x for my y. X equals 3y plus 5, and to get it in function notation form, I now have to solve for y to get the inverse f of x function. Y is going to be equal to x minus 5 all over 3. The inverse function of x is going to be x minus 5 over 3. If we have f of x equals x squared, again, what I'm going to do is I'm going to change that into y equals x squared form, and I'm going to swap my y with my x, so now that's x equals y squared, and solve for y. So if x equals y squared, I'm going to solve that for y. I just have to take the square root of both sides, and I'm going to get y equals the square root of x. To practice what we learned tonight and review what we did last night, I'd like you to work on this worksheet. Take a look at more function notation tomorrow. Have a great night, everyone.